In the last class, we were talking about decision trees, and we have talked about entropy and information gain, which are very relevant to decision tree. Okay, so what we know about information gain, that it measures the relative it measures the relative entropy with respect to some feature or attribute. Okay, and as I said in the last class that we will be talking about Gini index as a different splitting parameters. So that can be used in classification tree and regression trees algorithm. So in this context, we can introduce the Gini index. So here the Gini index is used in classification trees as an splitting parameter. Okay, this is sometimes called Gini index, or sometimes it is called Gini impurity, because it measures the impurity in a feature. Okay, so now what is Gini index? So Gini index, let us consider that we have selected a feature randomly. Okay, and we try to measure the probability of this feature which is classified incorrectly. Okay, so therefore it gives the amount of probability of a specific feature that is classified incorrectly when it is been selected randomly. Okay, so if all the elements are linked with a single class, then it is called pure. Okay, so since the Gini index measures the purity in a feature, so therefore if all the elements are found to be belong to the single class, then it will be called pure. Okay, now when we measure the Gini index, we will take the probability between 0 and 1. Okay, so when Gini index tends to 0, that means the probability of having purity in that feature is getting increased. Okay, and when the Gini index is found to be tends to 1, that means the randomness or uncertainty is found to be maximum. Okay, so when we get the Gini index 0, we can say the feature is pure. That means all the elements belong to the same class. Okay, that means only in the data set there is only one class. Okay, and when the Gini index is found to be 1, then we can infer that there is an impurity. Another way we can say that the randomness or uncertainty is found to be maximum. Now how to calculate this Gini index? So we can calculate the Gini index, which is given by 1 minus summation over I equals to 1 to n. Okay, we take the square of pi. Now what is pi? So pi is the probability of an element. Okay, so here pi is the probability of an element. Okay, and this summation over square root of pi gives us the probabilities of each class. Okay, probability of each class. Suppose in the data set we are having two classes, class A and B. Okay, so therefore we will calculate this Gini index for class A and B. Okay, and then we will take the summation, and this summation will get subtracted from 1. Okay, so this is the measure of Gini index. Now, when we design the decision tree, so the features which are having the least value of the Gini index will be preferred. Okay, that means when we select the root node, so obviously we will going for the feature which is having the least value of Gini index. But in case of information gain, what we found that we take the feature which is having the maximum value of information gain. Okay, so this is the basic difference between Gini index and information gain. And we can have two more differences, that Gini index works on bigger distribution, okay, whereas information gain works on small distribution. So this small distribution will be having small count with multiple specific values. Okay, so Gini index works on bigger distribution, and information gain works on small distribution. And another thing is that the Gini index operates on the categorical target variables, and this performs only on binary split, whereas information gain computes the difference, compute the different entropy before and after the split. Okay, so here we get the categorical we target on the categorical variable. Okay, when we compute the Gini index, and when we compute the information gain, so information gain computes the difference entropy before and after the split. Okay, so these are the two other differences between Gini index and information gain. So you should remember one thing, that when we select the root node, so root node with information gain, so we will select the features which is having the maximum information gain. Okay, and when we will select the root node with Gini index, so we will go for the feature which is having the minimum Gini index. Okay, now what are the steps that we follow to construct the decision tree? Okay, now we can have a number of steps. The first steps that we need to, let me write the steps. Create the root node. So first we create the root node. This is the first step. And in the second step, we will check if all examples are found positive or not. If they are found positive, then it will return, the lib node will return positive. Okay, lib node will return positive. Otherwise, if all examples are found to be negative, then it will lib node will return negative. Okay, what is the next step? In the next step, we calculate the entropy of the amount of state. Okay, so next we calculate the entropy on the entire data set. Okay, so data set of entropy is calculated in the next step. And in this step, for each attribute or feature, so for each attribute we calculate the entropy. We calculate the entropy with respect to the attribute, with respect to the attribute, let's say x, okay, denoted by h of, that is entropy of dataset S and comma x, okay. So in this step, for each attribute, we calculate the entropy with respect to the attribute x denoted by h of s comma x, okay. And in the next step, select the maximum value of, select the maximum value of information gain, okay, information gain over s comma x, okay. And then we remove the attributes that offer highest information gain from the set of attributes, okay. Then we remove the attribute that offer highest information gain, okay, highest information gain. And in the final step, we repeat until we run out of all the attributes, okay. So we will repeat this first 7 steps until and unless we run out of all attributes. So these are the steps by which we can construct a decision tree based on the feature values, okay. Now let us consider an example, okay. Let me show you a data set. Can you see the data set? So here
Yes, sir.
here you can see the data
Yes,
set,
sir.
okay. And we have collected this data set uh, uh, over 14 days about the weather, okay. And in this data set there are 4 attributes. One is the outlook, temperature, humidity, and wind, okay. And there is a class attribute also, okay. So based on the combination of these feature values, we will decide whether we will play the golf or not, okay. So in this class attributes there are only 2 decisions, either yes or no, okay. So since here consecutive 14 days, the weather of 14 days are given, so based on these attributes or and their corresponding attribute values, we will find the combination. We will find the combination, and for a particular day when we find that combination, so we can decide whether we can play the golf or not, okay. So this is a basically predictive modeling problem. So in this predictive modeling, we have to predict whether we can play the golf or not, okay, on a particular day. That means if we try to find the combination on day 15, okay, then we have to train the predictive model using the existing data set, okay. And obviously various combinations of features values and using that trend model, we can we can predict whether we can play the golf or not, having some feature values for outlook, temperature, humidity, and wind. Okay, now let us try to. So here you can see that how many classes belong to no and how many classes belong to yes. So here you can see that here we are having 1, 2, 3, 4, 5. That means number of no. Here we can have the number of no class is 5 and number of yes class is 9. Okay, and total number of classes is 14 and total number of classes is 14. Okay, now can you tell me what will be the entropy over this data set S? So we have to now calculate the entropy, because we need to have the information gain, and before we compute the information gain we need to calculate the entropy of the data set. Okay, so how to calculate this entropy? So we know the equation of entropy. So we will take 9 by 14. Okay, that means probability of having the yes will be 9 by 14. Okay, then we will take log of 9 by 14. So pi log of pi. Okay, so minus pi log of pi. So here we will get 5 by 14. Okay, and log of 5 by 14. Okay, and this will give us some values. Now let us consider we are going to calculate the information gain for a particular feature. Let's say wind. Okay, so here so for this attribute or feature we can get the information gain. So we can calculate the information gain over s comma, we can write wind. So how to calculate this? So what we know about the information gain is that, so we can get the summation I equals to 0 to n probability of element x. Okay, which is multiplied with hx. Now here x is the possible value. So how many values are found in case of the attribute wind? So here we can have two different values. One is the weak, another is strong. Okay, now we need to observe that how many if the wind is found to be weak, then what will be the decision, and if the wind is found to be strong, then what will be the decision. That means for both weak and strong we can get the class information as yes and no. Okay, so in this case we need to in this case we have considered the attribute wind. Okay, and we have two values. One is the weak, another is strong. Okay, and how many weak values are given? So let us calculate 1 2 3 4 5 6 7 8. Okay, so we can get 8, total 8. Okay, and if we calculate the strong, that means out of 8 8 is having weak value. Okay, and out of 14, 8 is having weak value, and out of 14, 6 is having a strong value. Okay, now here we need to also consider the total number of positive and negative decisions that are coming out for the wine to be found weak and wine is found to be strong. Okay, so in that case we need to calculate the probability of, place of, we can write the weak. Okay, and probability is of, we can write strong. So how to get that probability? So for probability of S of weak, we can get 8 by 14, and probability of strong is found to be 6 by 40. Okay, and then we get the entropy. We get the entropy. So here, we get the number of weak values. So here the number of decision for weak values is 8. Number of decisions for strong values is found to be 6. Okay. Now we compute the probability over weak class and probability over strong class. Okay. So here since there are 8 decisions for weak values, so therefore we will get the probability over weak 8 by 14 and probability over strong 6 by 14. Now we will compute the entropy for weak values. Okay, so how to get that? Now here we need to see how many decisions are found to be positive and how many decisions are found to be negative for weak values. Okay, so here we can get how many decisions are found to be positive. Let's say here 1 2 3, then 4 5 and 6. Okay, so here what we will write? We will write 6 by 8 log of 6 by 8. Okay, minus.
Sir, page is not visible.
Okay.
Next page.
Okay.
Yes, sir. Now
so here you can see that.
Yes, sir.
Entropy, after getting the probability over weak variables and strong variables, now we will get the entropy. Okay, entropy over weak. So entropy over weak means 6 out of 8, 6 are having yes decision and 2 are having no decision. So therefore we get the entropy over this weak values, which is given by minus 6 by 8 log of 6 by 8. Okay, minus 2 by 8 log of 2 by 8. So this will give you some value. Okay, so this value is referred by entropy over weak values. Okay, now we will get the entropy. We will get the entropy over strong values. So here we need to see how many yes decisions are coming for strong values and how many no decisions are coming for strong values. So let us see the database again. So here we can see that let us consider. So strong, how many strongs are found? 1, 2, 3. Okay, so 3. So here we can write minus 3 by 6. That means out of 6 decisions, 3 decisions are found to be yes for strong values. Okay, and rest of the 3 out of 6 are found to be no for strong values. So therefore, what we can write? We will write 3 by 6 log of 3 by 6 minus, and for rest of the no decisions, so 3 by 6 log of 3 by 6. Here you can see that entropy for strong values are given by minus 3 by 6. Okay, this minus 3 by 6 log of 3 by 6. So out of 6 decisions for strong values, we are getting 3 as yes and rest of the 3 as no. So therefore we compute the entropy which is given by minus 3 by 6 log of 3 by 6 minus 3 by 6 log of 3 by 6. Okay, so this will give you some value. So you have to remember this value so that it can be used in the next iteration. Okay. And finally we will get the information gain. Next we get the information gain over s comma y. That means information gained will now be computed for the attribute y. Okay, and this is given by h of x summation over. So here we can write I equals to 0 to n px. So we can write px. Okay, h of x. Now information gain over s comma y, which can be further written as h of x minus probability of s of week plus h of. Okay, this probability. So what we can write? The probability of s of strong. Okay, into okay h of x minus probability of, this is multiplied with h of. Okay, minus probability of s of strong, which is multiplied with entropy value. Okay, so this is the final derivation for the information gain which is computed for the data set with respect to attribute wind. Okay, so that means you this h of x is known. You have already computed this entropy value over the entire data set, and then you have computed the probability of having weak values. Okay, and then you have computed the entropy over these weak values. Okay, and this will be added with probability of having strong values, and which is multiplied with the entropy over these strong values. Okay, so this will give us the information gain. Okay, now here we need to consider, so here we need to consider the other attributes or features like outlook, temperature, and humidity. Okay, so the similar way we can get the information gain for outlook. We will get information gain over temperature. Okay, we will get information gain over humidity. You have already computed information gain for wind. Okay, now having this four information gain, now why we are going to compute this information gain for all the attributes? Because we need to first select the root node. So which one will be considered as root node in the decision tree, so that to be decided there. That is why we are interested to have this information gain values for each of these attributes and or features. Okay, so once we compute the information gain, so this information gains will give some values. Okay, so based on the, let's say the values are v1, small v1, v2, v3, and v4. So after calculation of this information gain for attribute wind, for outlook, for temperature and humidity, let's say the values are coming as v1, v2, v3, and v4. Okay, so v1 is coming for the information gain which is computed for wind. V2 is coming for the information gain which is computed over outlook, and V3 is coming for information gain which is computed for temperature, and V4 is coming for information gain which is computed for humidity. Okay, now the basic assumptions about the information gain is that we need to select the features. We need to select the feature which is having the maximum information gain. Okay, now out of these four information gain values, so which one is to be selected for the root node? Okay, so here we are having four values. So now among these four values, so one feature will be there out of wind, outlook, temperature, and humidity. So that will give us the maximum information gain. Okay, and the feature which is having the maximum information gain will be selected as the root node of the decision tree. So this is the basic step, so that we have to determine. Okay, so with this basic step we can compute the feature which is having the maximum information gain which is to be selected as the root node. So now root node is selected. Now what we will be doing, so let us consider the wind is selected as root node. So what will be our next step? So what will be our next step? So in the next step, so how many values are present in this column? Can you tell me? How many different values are present in outlook? How many different values are present in temperature? How many different values are present in humidity? And how many different values are present in?
Sir, in outlook, sir, three different values are present.
Very good. And
Sir,
temperature?
so temperature, So also 3.
Okay, and humidity
So 2.
and wind
So wind 2.
2. Okay, that means if I select the wind feature as a root node, then how many branches will be there? How many branches will be formed in the decision tree? So we have started with the root node
So
1.
2, 2, 2.
Very good. So one is level Y. So one will be weak, another is
Strong.
okay. Now if I
So the page is not visible.
okay, okay,
So next page.
okay, here you can see that.
Yes, sir. Yes.
Okay, so if I select the if I get the wine feature or attribute as the root node in the decision tree, then there will be two branches. Since there are two different values are present in this attribute column, so therefore there will be only two branches. Now if I get the outlook as the root node, then how many branches will be possible? Outlook,
So 2.
why two? There
So
are three
outlook so
different.
3, 3, 3.
So what are those branches?
So please show the list.
Yes, here.
So
You can,
sunny, overcast, and rain.
very good. Sunny, overcast, and rain. Here you can see the values for outlook. So if I have the outlook as the root node of the decision tree, then outlook will be having three branches. One is the sunny, overcast, and rain. So these are the different values of outlook attribute or outlook feature. Okay. Now what we do, we have already computed the information gain, then we have selected one information gain for a corresponding feature, and that feature becomes the root node of the decision tree. Okay, so up to this it is clear to us. Now after selecting the root node, so what will be the next step? What will be the next step? Can you tell me? Now we will go for a particular feature value. Let's say if I select the outlook as the root node, and there will be three branches, sunny, overcast, rain, then for this particular feature value sunny, we will repeat the same process. Okay, we will repeat the same steps which have been repeated for computing the information gain. Okay, now everything we will now in this case the data set is found to be narrow. Okay, that means uh, initially we work for the entire data set. Now we will work for a subset of the entire data set. Okay, and same process we will repeat, and same process we will repeat for getting the information gain, so that further we can divide this attribute sunny, overcast, or so among this sunny, overcast, rain, we have to select which one will be the root node of the subtree. Okay, let's say so for these three outlook values, sunny, overcast, rain, we will compute the information gain. Okay, so after having after information gain for sunny, out overcast, rain, so now we will check uh, which attribute value will give us the maximum information gain. Okay, and according to that we will go for the selection of the root node for the subtree. Now here Let's say we have selected the root node as outlook feature. Okay, and for this outlook feature, and if we look at the feature values sunny, then for this, so here we need to cut down the entire data set, okay, and make it a subset. So how can we make the subset? Okay, so here we can get how many rows are found for sunny? Can you tell me how many rows are found for the outlook value sunny? So here we can have 1 2 3 4 5. So with these 5 rows, okay, with this 5 rows corresponding to this outlook value sunny, we will construct a data set. Okay, so that data set will be a subset of the entire data set, and over this subset we will, that means for later here we can consider d1, we can consider d2, okay, we can consider d8, d9 and d11, and with these 5 rows we will get a new subset of the entire data set. So which will be having the other features like temperature, humidity, wind, and obviously there will be a attribute decisions, okay, attribute class values. So with this subset, again we will repeat the process. So let me show you. So in that case, we will not consider the attribute outlook, because we have already selected the outlook as the root node. Okay. Now for since there are 3 branches which are coming out from the outlook root node, therefore for a particular outlook value, let's say sunny, we can have this data set. So data set will be constructed in this way. So we will have temperature, humidity, wind, and play, whether we will play golf or not. Okay, so here you can see that now we are having 3 attributes: temperature, humidity, wind. Okay, and we have discarded the outlook attribute. So we are not taking this attribute. Since we have already selected this attribute, outlook attribute as the root node, so therefore we will not be considering this attribute outlook. Okay, but for a particular value of the outlook, we will make this make this subset of the entire data set, having which will be having the attribute temperature, humidity, wind, and the class attribute play golf. Okay, now over this small data set or subset, we will compute again the entropy, okay, and information gain. So all that we will compute, and then we will decide among this among these three attributes: temperature, humidity, wind. So which attribute will become the root node of the subtree? Okay, root node of the subtree, and accordingly we will expand the decision tree to the down. Okay, so I will give you a problem statement. I will send a problem statement today, and so you can try that problem statement. You can try to solve that problem statement using decision tree. Okay, So I will send that. Now we will be talking
Sir, through
about
email.
the yeah.
Okay, sir.
Now we will be talking about the random forest. Now what is random forest? So random forest consists of several decision trees, so which can be merged together in terms of their output to improve the performance of the model. Okay, so uh, if we model a problem with random forest instead of decision tree, then we can have a number of decision tree. That means we can combine a number of decision trees together and we will get the random forest. Now when we merge the decision trees together, so so this merging will be done, or this we will fuse these decision trees in terms of their outputs. That means if we consider there are n number of decision trees t1 to tn, then every decision tree will generate some output. Let's say output is y1, okay, y2, yn. So what we will do in the random forest? So for every decision tree, we will get the output as yi, okay. And after having n number of output which are generated from n number of decision tree, we will go for combine these outcomes y1 to yn, okay, combine, or we can say fusion, okay, so that the fusion result can enhance the performance of the predictive model. So we can use this random forest as classifier as well as a regression model. Okay, so when we design a predictive model using random forest, so we will create n number of a number of decision trees, and we will compute the decision trees for n number of outcomes, and whenever we get the n number of outcomes, we will go for the fusion of this n number of outcomes. Okay, now how we can achieve the fusion? So this is nothing but a linear combination of these decision trees, individual decision trees. So if we talk about the fusion of decision trees, then we can have two different choices. One is bagging, okay, or sometimes we can say bootstrap bootstrap aggregation, okay, bootstrap aggregation. And another choice that we can have is boosting. One is bagging, another is boosting. Now when you see so these are the two combinations rule or ensemble rule. Sometimes we can say ensemble rules, okay, these are the ensemble rules. So we can use any one of these two ensemble rules, and we can combine or fuse the individual decision trees together and get the enhanced performance, okay, for a particular predictive model. Now uh, how bagging is used? Now whenever a decision tree is trained on the random subset of data samples, where the sampling is done with the replacement, okay, that means for each and every decision tree ti, so we will have a small data set, okay, we will have a small data set. Let's say the small dimension of this small data set is p, and the dimension of dimension of, let's say, dimension of the original data set or the uh, entire data set is Rm, and dimension of small subset is Rn. Okay, so obviously Rn will be found to be less than Rm. Okay, so we can generate these small data sets over random sampling. Okay, where we can make the replacement of the samples, or we can choose a particular attributes without overlapping, and then we can get the subsets, and we will train the subsets. We will train the decision trees, individual decision tree Ti, with this subset of data set, and then we get the decision for every decision tree Ti. Okay, and finally we will ensemble the outcomes of these decision trees using bagging and boosting. Okay, so bagging, in bagging, decision tree is trained on the random subsets of data samples, where sampling is done with the with replacement. Okay, so how bagging is works? If we if we talk about the bagging or bootstrap aggregation algorithm, then we will see that it works parallelly. Okay, so it works parallelly. So this is the first. This is the first. We can say uh, this is the feature of the bagging algorithm, and second point is that it accepts features bagging. Okay, and it selects only a random subset of important features at each split. That means whenever we go for splitting the data, okay, and we will select the important features, and it also reduces the correlations and impact of the very strong predictor entity. Okay, so, and it also decrease the variance. So these are the different properties of a bagging algorithm. When we apply this bagging algorithm for combination of individual decision tree, so we can enhance the performance of the predictive model. Now if i select if i select if I select the boosting, then how boosting works? So boosting works sequentially. That means boosting is boosting is an iterative algorithm where we adjust the weight of the previous decision tree, and get the weight updated in the weight updated in the next decision tree in the sequence. That means since bagging works parallelly and boosting works sequentially, so therefore when it will be presented in sequentially, so we can have T1 plus T2, T3, okay, and Tn. Now here T1 represent the first decision tree, T2 represent the second decision tree, T3 third decision tree, and Tn is the last decision tree. Now we do not take the linear combination of these decision trees, but we take the weighted combination of this decision tree. That means first we generate the output of individual decision tree from T1 to Tn, then with every outcome we will associate an weight. Okay, and this weight is determined according to the strength of this decision trees. Okay, so here with every outcome of the decision tree, we get multiply the weight values, which is determined from this sequence of decision trees, and then we get the linear combination of outcome and weighted values. So whenever we get the weighted value for T1, then this will be propagated to the next decision tree T2 in the sequence. Okay. So first we get the weighted value of the output for T1, then we get the weighted value of the output for T2 using the previous weighted value of T1. Okay, that means when we arrange these outcomes, weighted outcomes sequentially, then we can see that T2 depends on the T1, T3 depends on the outcome of T2, T4 depends on the outcome of T3, and Tn will depend on the outcome of Tn minus 1. So in this way we arrange the outcomes of the decision tree in linear combination of outcome and weight values, and we use the weighted outcome of the previous decision tree in the current decision tree so that we can update the weight values. Okay, we can update the weight values and we get the final decision, which is the outcome of the random forest for n number of decision trees. Okay, if you have any questions you can ask me, otherwise in the next class we will be talking uh, in more details about bagging and boosting algorithm. Okay, if you have any questions you can ask me, otherwise we will stop now.